Hi everyone, we are back and we are going to set up and actually start to solve a static equilibrium practice problem. Now, we are going to develop our statics problem solving algorithm. And this is a general algorithm or way to approach a problem for really any class. So the first thing we're going to do, we're going to read the problem, but then we're going to idealize our real system, meaning we're going to make some critical assumptions, some critical idealizations. Then we're going to define our coordinate system. We're going to draw a free body diagram, meaning there's a particular body where forces are being acted upon that body. So we are going to take our schematic or our diagram or our real system, and after we make those idealizations, we are literally going to free, in this instance, there's a body, which is the mass, the mass that's being hung by the cable, and we're going to free it from the surroundings, meaning I'm just going to draw the body that's being, and then there's a force that's being acted upon here, and a force that's being acted upon my weight and the tension here. This would be the free body diagram for that system. So I'm freeing this body. This is no longer a cable. It's just a force representation for the tension. And this is a force representation for the weight, and it's acting upon a singular point. So I'm freeing it from my surroundings. So free the body from the surroundings. We must draw this free body diagram. It is not just so that we can be mean as instructors. It's not an academic exercise. It is literally one to help you solve complex problems, to make and reduce problems in terms of complexity, but also to communicate how you solve the problem. Then we're going to write out our equilibrium expression. Some of the forces must be equal to 0. Some of the moments must be equal to 0 about some origin. And we're going to solve for whatever our unknowns that are remaining. So let's look at a fun problem here. Consider the situation: a person with a mass of 100 kilograms, scaffold that's suspended by 2 cables here, and we see our problem. So what are we looking at here? So we have a mass of a person. We have 2 cables. All right. So first, let's make some idealizations. We have basically the scaffold is effectively this beam right here. So we are actually going to say and neglect the mass of the scaffold itself. We're also going to ignore friction in the scenario. So there's no friction forces between the person, they're just standing on it. And we're going to neglect the mass of our cables as well. So those are the big idealizations, and we're going to assume everything is rigid. So that takes care of step 1. We've idealized the real systems. Our coordinate system is going to be just simply this. We're looking at this for plus. Now I'm going to draw my free body diagram. So my body is the scaffold. There's going to be, at this location, a force, which is weight, and the weight is just going to be simply the mass, which is 100 kilograms. So mass equals 100 kilograms, times 9.8 meter per second squared, and that's going to give me a Newton. Again, that's just G, 9.8 meter per second squared. There's also, over here, a tension 1 and a tension 2. Now, this problem is pretty apparent, like where the tension is pointing, but your direction here, it really doesn't matter. If you get this wrong and you'd get a value that's negative, you would just have to flip the sense of the direction of these arrows. So you shouldn't have to be too worried about it when you're doing these statics problem. It all comes out in the math at the end. Fantastic. So we've drawn our free body diagram. Now we need to write our equilibrium expressions. So what's the sum of the forces in the x direction? Well, we're in static equilibrium, so they must be equal to 0. Are there any force in the x direction? No. So everything's fine there. What about some of the forces in the y direction? Well, it must be equal to 0, so we'd have T1 plus T2 minus W. Okay, this is still an unknown. This is still an unknown. Now we need some of the moments. About an origin will make it equal to 0. Now, where's our origin in this problem? When I'm doing a moment, I can set up my origin at any location because the sum of the moments everywhere must be equal to 0. Strategically, you want to put your moment at one of the force values or at a location where there's multiple forces. Why? Let's say I put my moment at position 1. What's the perpendicular distance from my origin to the line of action for T1? It's 0, right? So there's no moment from T1, but there is a perpendicular distance to the line of action to W, and that is 2 meters. And if I do my right-hand rule, I can see that it's going to be minus W times 2 meters. What about to T2? That's 10 meters, and I see that's positive because it's going to go counterclockwise. So I'm going to do plus T2 times 10 meters. And that must be equal to 0. So I have 2 unknowns. I have 2 equations with actual variables. Let's go ahead and solve. I'm going to click my kernel. And I'm going to say my W, let's say, mass equals 100, G equals 9.8, weight equals M times G. I'm going to say my Fy is equal to T1 plus T2 set equal to 0. And my M1 equals minus W times 2 plus T2 times 10 meters. Set that equal to 0. I'm going to solve. I'm going to solve for what is Fy? M1. Solve those 2 equations simultaneously once Mathematica wakes up. 2 equations, 2 unknowns. Come on. It's exciting. It wants to run. There we go. And we see, oops. Let's see. So, and why are we getting a negative here? Because I went too fast. I need to do minus W. Here, here, and voila. Now, does this make sense? Kind of. I mean, yes, it does, actually. I mean, mathematically, but also the tension here is going to be a little bit heavier because, again, this is not equidistant, right? Again, I'm opposing essentially this force here. So, we've just solved our first statics problem. Congratulations. So, now, let's move on to the next one, which is going to be our seesaw problem. We'll see you then. Thanks. Bye.